In this video, we're going to learn how to simplify rational expressions. So just to recap, what's a rational number? It's just a fancy way of saying it's a fraction. So it's any number that can be written in this form here with a numerator divided by a denominator where these are m and n are integers. So working with fractions, there's one really important rule, which is that the denominator of a fraction can never be equal to 0. And that's because we can't divide by 0 because we don't know what happens to a number when it's divided by 0. So if we take a look at 0 divided by 4, that means if we're talking about Smarties, let's say, we've got 0 Smarties divided by 4 people. How many Smarties does each person get? Well, there's no Smarties, so that has to be 0. So 0 divided by a number, we can understand what happens there. But what if we have 4 Smarties divided by 0 people? What happens to that? You might think, oh, well, there's 4 Smarties left. But if we take 4 Smarties and divide it by one person, that's how we get 4. So what is 4 divided by 0? We have no idea. So we cannot divide by 0. When we do, the solution is called undefined. So that's the most important rule when we're dealing with rational numbers. Now, today we're talking about rational expressions. Rational expressions is just when we have a fraction and we have a polynomial on the top and a polynomial on the bottom. So here's 3 examples of what they could look like here. Something that we're going to be asked constantly when we see a rational expression is to come up with the restrictions on the variables. So restrictions are just what is x, or whatever letter we're dealing with, allowed to be, and what is it not allowed to be. So restrictions actually are specifically what are the variables not allowed to be. What values can they not take on? And that all comes from the rule that we cannot divide by 0. So if we take a look at this first example, we're asked to find the restrictions on the variable. So in this case, our variable is x. And so remember that the denominator cannot equal 0. There's no rule about the numerator. We know that 0 divided by 4, that's just 0. There's no problem with that. So the numerator can be 0. So when we're looking for restrictions, we don't care about the numerator at all. We just look at the denominator. And can you tell right away, what could I plug in for x here that would make the whole thing equal to 0? If you think that you know, that's wonderful. If you need to do a little equation, just say, well, what if this thing equaled 0? So we're just going to put a cross in there. And just remember that x plus 2 cannot equal 0. And we're going to just solve this as if we have a normal equal sign. That just means x cannot equal -2. So that is what the restriction is. Notice that our restriction did not come from the numerator. X can equal 3. If x was 3, it would be a 3 minus 3, and the numerator would be 0, which is not a problem. Let's try this next example here. What are the restrictions on this rational expression? Again, we don't care about the numerator. The numerator can be anything. We care about the denominator. And here we have 2 different parts of this expression here. We have x, and we have x minus 4 all squared. So what can't x be here? Remember, each little factor here cannot equal 0. So x cannot equal 0. That's the first restriction. Because if this was 0, it would be 0 times anything is going to be 0. So that's our first restriction. How about this one? X minus 4 cannot equal 0. So what can't x equal? X cannot equal 4. So here are 2 restrictions. X cannot equal 0 or 4. And we're done. Just a side note, the squared does not change the restrictions, because if we were to expand this all, this is just x minus 4, and then x minus 4 again. So we still have the restriction of 0, done, 4, and then just 4 again for a repeat. So that squared doesn't actually change our restrictions. How about one with a double letter? So we've got 2 letters here. We've got x and we have y. So let's try doing the restrictions for x here. So we get to something we're not sure how to do. What do we have to do? Well, what did we do for the other ones? We just made these little equations and said that these things cannot equal 0. So I can choose to isolate for x here or y. I'm going to choose to isolate for x, and let's just see what happens. So 2x cannot equal y, and then if I divide by 2, x cannot equal y over 2. So there's our first restriction. I'm going to take this one now, and let's find the restriction here. X plus y cannot equal 0, and I'm going to isolate for x again. So we have x cannot equal negative y. So our restrictions for x are that x cannot equal y over 2 or negative y. So implied here are also our restrictions for y. So we can, when we have two letters here, we can either choose to isolate for x or either choose to isolate for y in each binomial. Now, if there was like a y here, for example, we'd have to include the restriction of y equals 0. But let me show you another way you could have done it. Instead, we could have taken these exact same expressions and just isolated for y, and we're going to get an equivalent statement. I'll show you what I mean. I'm going to put the y on the other side here, and there's our first restriction. Y cannot equal 2x, and I'm going to do it again for this one. We'll do it in blue. So we're just isolating for y instead. So this cannot equal 0, y cannot equal negative x. And so if I were to summarize this, that means that y cannot equal 2x or negative x. So both of these are perfect answers, and they're equivalent to each other. They're saying the same thing. They're just rearranged. Okay, so you can say this or you can say this, but these are actually saying the same thing. Now we're going to start simplifying these rational expressions. And before we do, we need to make sure that we really understand a very important concept, which is this rational expression versus this rational expression. Now this is just an example of putting in an x value of 3 into this rational expression. So there's not much different about these, but we can see some common mistakes that students will make. So for example, once we start simplifying these, we're going to start crossing out numerator and denominator common factors. So something common students do are cross out these x's. So crossing out these x's, and then we'll see something like this, 5 over 1, and that just equals 5. So that works out really nicely, right? So to know if we're actually allowed to do this, let's try it with actual numbers and see if this makes sense. So let's just simplify this the way we know to do it. 3 plus 5 is 8, 3 plus 1 is 4. So this answer should be 2. So we can simplify it other ways. There's also ways to simplify one thing, but we know that the answer should be 2. So I'm going to do exactly what I did on the left side here, which is I'm going to cross out these 3's. We have 3 divided by 3, right? And then so we're left with 5 divided by 1, which is 5. Did we do this correctly? The answer should be 2, but we got 5. So what we've learned here is that you cannot do this. This is not 3 divided by 3. This is an adding 3 dividing by an adding 3. We're only crossing things out when we're using opposite operations, when we are multiplying and dividing by the same number. So when we see adding and subtracting, we cannot be doing this. The only time we can cross things out is when it looks like this. If instead it were multiplying, that is when we can cross out those 3's. Then this is times 3 divided by 3, and that is going to be 1. So in this case, we can cross out the 3's, and our answer will be 5. But we cannot do this. We cannot do this. So if we see things are adding and subtracting, we cannot take a part of it and cross out another part of it from underneath. So we're going to keep that in mind as we try to simplify our first rational expression. So we're asked to simplify this guy, and then we're going to state restrictions on the variables. So the reason why it was really easy to state restrictions on these variables is because everything was factored. So you can't simplify, or you can't state restrictions until the very end, until we have everything factored. So to simplify a rational expression, we are not going to make that mistake that we just did. I'm not crossing out that n3, n3. That's the same mistake that we just did above. We need to factor this so that we can see, so we can get everything multiplying on the bottom and everything multiplying on the top, and then we might be able to cross out. So when you get irrational expressions with two unfactored expressions on the top and the bottom, just take them to the side and factor them separately. So I'm going to factor 3n cubed minus 3n squared. And I know I can factor this with common factors, so I'm going to take a 3n squared out. I'll be left with n minus 1. For the second one, we've got 8n cubed minus 12n squared plus 4n. I can take out a 4n, and I'll be left with 2n minus 3n plus 1. I'm going to quickly factor with decomposition. We're looking for two numbers that multiply to 2 and add to negative 3. So it's got to be negative 2, negative 1. We're going to quickly change this. And then we're going to group them. Oh, I'm missing a squared here. There should be a squared here, a squared here. Here we go. And then I'm going to take out a 1 here. Almost done. One final step. And here is what it factors to. So once you have everything factored, we're going to put it back together into our equation. So we have this function. We called it g and n. And the numerator factors to 3n squared n minus 1. And the denominator factors to 4n n minus 1, 2n minus 1. So now that everything's factored in the top and everything's factored at the bottom, we're dealing with all multiplication here, multiplication, multiplication. Now we can start canceling things out. So the 3 over 4, think of that as a fraction 3 over 4. It can't be simplified anymore. But let's take a look at these n's. We've got two n's at the top, one n at the bottom. So using exponent laws, we're going to be left with one n at the top. So let's start writing down what we're going to have left over. So I'm going to write my fraction bar. I have a 3 and a 4. That's still there. When we simplify this, we're going to be left with 1n up at the top. That's just using our exponent laws. And now I also see I have n minus 1 divided by n minus 1. So this is times n minus 1 divided by n minus 1. So those are going to cancel out. So those guys are gone. And we're still left with a 2n minus 1, and it's at the bottom of the fraction. So we've got 2n minus 1. So nothing else can be further simplified. It's not going to help me to expand, so don't expand. We did all that work to factor it. Let's leave it factored. So now that nothing else can be simplified, nothing else can be crossed out, we're just left with coming up with restrictions. So we're going to come up with what n is not allowed to be. So let's make a list. So what can't n be? So when making restrictions, you have to start at the top and work your way down. The restrictions don't just occur at the end of the problem. It happens throughout the problem. Now before it's factored, we can't find the restrictions. So forget about here. But here it's factored. We don't care about the numerator, we just care about the denominator. So what can't n be? Let's look here. If we set 4n equal to 0, we find that n cannot be 0. Because 4 times 0 would make the whole thing 0. How about here? If we set this equal to 0, we'd find that n cannot equal 1. And then this one, if we set this guy equal to 0, we'll find that n cannot equal a half. So this is a simplified rational expression with the restrictions. Let's take a look at another one. Here we have a monomial divided by another monomial, so there's no factoring necessary here. So all we're doing is we're just simplifying because everything's already multiplying. So I'm going to start off with my fraction bar here. I'll keep my negative on the outside. And then let's deal with these numbers. So 30 divided by 6. So 30 divided by 6 just simplifies to 5. So I'm going to rewrite that as 5. Next, I can deal with my x's. So I've got 4 x's at the top. So imagine x, 4. And then we have 7 x's at the bottom. How many x's will we be left over with? Well, we're going to have 3 left over, and they're all going to be at the bottom. We're just using our exponent laws. We've got 4 on the top, 7 at the bottom. They're all going to cross out, and we're going to be left with 3 at the bottom here. And then now with the y's, we have 3 y's at the top, 1 y at the bottom. So there's going to be 2 y's left over, and they're going to be at the top. So this is as simplified as we can get. So now we have to make restrictions. So again, we just care about the denominator. So let's do with x first. So what can't x be? Well, x can't be 0. If we set this equal to 0, x can't be 0. Now in this case, we do have to do restrictions for y because they're not a part of these restrictions for x. So we haven't accounted for y yet. So we also have to do restrictions for y, and y's restriction is also cannot be equal to 0. When we look down here, again, x cannot equal 0. It's already included. So we're done. I might have forgot to mention that on the other question, by the way. When we were doing the restrictions here, I did them from this line here, and I should have mentioned this one that's left over is still n can't equal a half, and it's already included. So just start from the top and work your way down and just make sure all the restrictions are included. So let's try 2 more. Let's try this guy. So on your own, factor the top and the bottom of this fraction and then come back. If you're back to the video now, you have the top and the bottom factored. So here's what your expression should look like. Notice that you can use decomposition for this one, but once you find your factors, remember you can use the shortcut for this because the a value, so the number in front of x squared is 1, you can just take these numbers and pop them in this way. So copy down the x, put in the a, -1. So that's the shortcut for decomposition that we can only use when a is equal to 1. And so now what to do here? Can we cross these out? I'm looking at these two here. These look really similar, but are they exactly the same? No, but they're so close. They're so close. These are just opposite of that. So why don't we factor out a -1 here and see what happens? So I can't cross them out just yet because they're not exactly the same. But if I factor out a -1, this term will become positive x, and this term will become -1. And then look at that. Now they're exactly the same. And so now we can cross them out, and we'll be left with, on the top, we'll be left with x plus 8. And at the bottom, we'll be left with 2 times -1, which is going to be -2. One final step, don't leave a negative at the bottom of the fraction, so I'm just going to put it to the side there, just like this. And we are done. Last step, let's find the restrictions. So what can't x be? Starting from the top. Can't tell from here, let's start here. What can I put in for x to make this whole thing equal to 0? 1. Any other restrictions? Nope, 1 again, nothing here. So here's our only restrictions, and we're done. Last one, here we go. All right, so let's factor this thing. Okay, so let's factor the top. Are we freaking out that there's 2 variables? We shouldn't. We're just going to factor this using the techniques we know how to do. Okay, so factoring this guy here, we're just going to, this is just a difference of squares. So I'm going to take the square root of the first guy, that's just going to be 2x, plus or minus the square root of the second guy, which is going to be 4y. So I'm going to have 2x plus 4y and 2x minus 4y. How about the bottom? Okay, we're not freaking out because there's 2 letters. We're just gonna factor this with normal decomposition here. We're looking for 2 numbers that multiply to -6 and add to 1. What are the 2 numbers? Because there's a 1 there. So it's definitely something to do with 3 and 2. The 2 has to be negative. Okay, so here's how to deal with decomposition with two letters. Instead of breaking this up into 3x, we're going to break it up into positive 3xy and negative 2xy, and then keep copying the 6y squared. And so we're just going to common factor this like normal, group and common factor. So I'm going to take out an x, and I'm left with an x plus 3y. I'm going to take out a negative 2y, and I'm left with x plus 3y. So I'm still following the same rules of decomposition. We just got another letter tagged along. Okay, let's keep on finishing this guy up. So we've got 3x plus y in common, and we've got x minus 2y. Done. So now that that's all factored, we're going to put it all together. Our numerator is 2x plus 4y, 2x minus 4y, all over x plus 3y and x minus 2y. So looking at this, it doesn't look like anything can be factor or crossed out, huh? But I'm looking at this, 2x minus 4y, x minus 2y. Is there anything I can do to this to make it look like this? Well, we actually forgot something when we factored this. We forgot to common factor first. A 4 can be taken out of these. So let's finish common factoring this. So on the numerator, let's common factor out in this first guy here. So we can take out a 2, and then we'll be left with x plus 2y. And then let's common factor out a 2 here again, and we're going to be left with x minus 2y, and then we have all over our denominator. Okay, and now we can cross out. Okay, these two are going to go away. In the numerator, we're going to have 2 times 2 right here. The 2's and the 2, that's going to make 4. So we've got 4 x plus 2y all over x plus 3y. And we are done. Only step left is coming up with our restrictions. So let's determine whether we want to isolate for x or for y here, because all the binomials include x and y, so we really just need to do one or the other. So if I take a look at this one and I set myself a little equation, so if I take this guy and I set myself a little equation, x plus 3y cannot equal 0. It's easier to isolate for x here, so x cannot equal negative 3y. And if I make myself a little equation here, we have x minus 2y cannot equal 0. Again, x is easier to isolate for, so x cannot equal 2y. So those are our two restrictions. X cannot equal negative 3y, and x can't equal 2y. Again, it's the same restrictions here and here. Here, writing this, it also implies that y can't equal x over negative 3 or x over 2. So we have all the restrictions all in one line, and we're done.